Hello everyone. In this video, we'll be talking about a classical paper titled Asymptotically Efficient Adaptive Allocation Rules. Um, this paper was published in Advances in Applied Mathematics in 1985. This paper was authored by Lai&Robbins. This is a classical paper which introduces an important result which we'll be looking at. So, yeah, we'll move right into the setting. We have K arms as usual, 1 through K. You can assume each arm has a slot machine, and each arm gives you a reward which stays between 0 and 1. These are random rewards. So now arm I reward follows a distribution pi, and it is ID across every pull, and here we denote the average value of this reward as mu I, and then the pulls are independent. So I think these two are the same. Okay, then now moving on to the assumptions. These are just to make the proof simpler. For more details, you could look at the paper. You can assume all the mean rewards of all the arms are not equal. This is because you could just think of two arms with same rewards, mu and mu, as one arm, and that's about it. And the second assumption is that you could think that the first arm gives you the maximum reward among all the K arms. So now coming into the definitions, any online strategy selects an arm IT at time t given all the reward observations until time t. So you pull arms from time 1 through t. You observe some rewards here, x1 through xt. So based on these rewards, you select IT. So now for any finite n, we define the regret term Rn. This is the regret has the expectation of the summation of the difference between the maximum reward minus the reward which you would get by pulling the arm IT. So we already showed that we can rewrite in terms of the visitation frequency, or this is the number of times you pull an arm I until time n. So I'll link the video in which I prove this expression. You can gladly check it out. So here delta I is the difference between the reward of the maximum arm and the ith arm, so delta I. And yeah, so KL divergence, this is the normal definition. Yeah, the ith arm distribution is pi. This integral, you can assume that you are taking it with respect to the available density. The worst value that it can take is n times some constant. So any good online strategy should do better than this, and that is exactly this condition, that it should be in terms of it should perform polynomially in n. So yeah, so the result guarantees that any such good good online strategy satisfies this expression where it says that asymptotically Rn over log n is lower bounded by this term. So yeah, right, we'll directly jump into proving this result. So let's suppose we have this claim. It says that under the same assumption as this, for the suboptimal arm I, that we have the lim n of this expression is lower bounded by the 1 over the KL divergence. So if we have this claim, if we prove this claim, then it is straightforward that this result is true. So that follows from here. So that follows from the definition. So we can firstly from definition write this expression, and since we have assumed that limit exists, so we can rewrite in terms of limit. And so these are exclusive sums, so we can split the limit. So we have the step, and from the claim this follows, and this is exactly what the result was saying, the main result. So now the proof sketch of the claim. So we'll fix an arm, the suboptimal arm, to be 2, and by repeating the following argument for every other suboptimal arm, we would have proven the claim. So first we replace the the average reward of all the arms from mu1 through mu k to this part, where now the second arm mu2 prime is greater than mu1. So making this in this structure, now mu1 is no longer the optimal arm, so no longer optimal. So think this has some new distribution, following p prime, and this one follows the p, where p prime is nothing but the cross product of pi primes I, and likewise p is the cross product of pi's across p because of independence. And yeah, by choosing this mu2 prime is strictly greater than mu1, we can actually have this condition satisfied for some delta which is between 0 and 1, and it's greater than a. Yeah. So now under this construction p prime and p, now we'll follow using the assumption of the main result. So the main result says the regret term. This is the regret term because now the second arm is the optimal arm. The assumption says the regret term is order of n power a, and this term is equal to this term because see the summation of ti's summation of ti of n over all arms is nothing but n. So, and notice that this expectation is over p prime, the new constructed distribution. So now by Markov inequality we have this result. I'm writing this informally where there is some constant c of log of n. So yeah, nonetheless this is the this follows from Markov inequality. And now, as we said, we are fixing delta such that delta is greater than a. Now rearranging this term here, and we are using this result that we are using this result here. Okay, I'll have to just mark it down. Okay, let's see, using 1 here, this follows from 1 and this follows from Markov inequality. Yeah, and now here I have actually chosen specially constructed constant, so the constant which I'm handpicking. So this will make sense because of the assumption, because of the construction made here. So yeah, bear with these notations a bit. Yeah, so now with this result we can write it in a very succinct way. Taking this term to the RHS, we'll get this term and define an event Cn to be this way. And yeah, Cn is actually a subset of just having T2 of n minus this term log n. So, and that is the reason why this result follows. Let's indicate this as 2. Yeah, here I have to define what this is. Um, Basically, this LM is nothing but an estimation of the KL divergence. Estimator of KL divergence. So, which is shown here. It follows from the strong law of large numbers. Yeah. Here you can see that these samples are actually coming from the original distribution P, and we are just using P prime for our proof purpose. So yeah, so a lot of these techniques are actually comes into picture only in the proofs, and don't appear in the algorithm per se. Doesn't appear in the online strategy considered. So yeah, you can find these techniques in every other theoretical paper you encounter. So now for a set theory fact, which can be shown really easily, that Cn can be written in this way as well. So where n satisfies the um, number of number of arms. The number of times arm I has been sampled is ni, and we are equating to those exact values and having n2 condition to satisfy this part. And since t2 of n is equal to n2 here, this part and this part follows. So yeah, you could show this by a simple set theory argument. So now from construction of p prime we can write this by definition. Yeah. So here things are getting cancelled. This is a short notation. Because we could as well write this to be p2 of xj and cancel these things out, and if the things were discrete, and this would be summation. So now the step directly follows because ln2 is less than this part. Where because of this, because of star here, because of the star, this part follows. And now so notice that these events are actually Cn, a part of Cn, a part of Cn, a disjoint set in the Cn. So because of the disjointness property, we would get this. Notice that this turns out to be n power n1 minus a. Yeah. So as n tends to infinity, and since 1 minus a, a is less than 1, so this is 0, less than 0, so yeah. So now since because of the strong law of large numbers, we can prove much more stronger result which follows from these statistics that consider the NEI and maximize over this LI. Still it converges to the sample average, converges to the tail divergence, but now it's almost surely with respect to P. Yeah. So now this translates to this part by definition, by the definition of almost sureness. And now since delta is greater than A, this is true. And hence this follows, because this would be the subset of this would be the subset of this part, hence this result still follows. And recall that we have already shown P of C of n to go to 0 as n tends to infinity. So from 5 and 6, this follows. Yeah, this is because I can explain in terms of set theory again. Let's see. Let's take this event as A, this event as B. So now here A can be written as A union B. Sorry, can write it in terms of mutually exclusive events, and this is Cn, which okay, now this implies P of A is less than P of Cn plus P of A intersection B complement. This is the union bound, and this goes to 0. Sorry, this goes to 0 as n tends to infinity, and this can be further upper bounded by P of B complement, and which is nothing but which can be further upper bounded by the term 5, the p into 5, so which is going to 0 as and goes to infinity. So yeah, basically all these shenanigans were made because intuitively the suboptimal arm should take at most log and many samples for the online strategy to learn that the arm 2 is actually suboptimal. So, and this is telling that story exactly. So now more into the details. Remember that we had this by construction for the fixed delta. So now we can translate this to this by changing the constant, the K divergence constant. Now by Markov inequality again, so Markov inequality, we have this part. So now to end the discussion, since delta was arbitrary, the lower limit of the lim inf of this term satisfies this lower bound. Disregarding, we are moving into lim inf because of this term. So yeah, this proves the claim which was mentioned here. And hence we have proved the main result of this paper. So to end this video, so this is the converse result of every other achievable result which you could come up with an algorithm, like the UCB algorithm, which I had mentioned and proved in the other video, which actually achieves the order of log n, but doesn't actually achieve this constant. UCB doesn't achieve this constant, but there is another achievable algorithm which actually reaches this constant, and that algorithm is called Thompson sampling algorithm, which I'll put it in the description box so you can check it out later. So yeah, thank you guys.